Hello, today we'll be talking about the ideal flow based on random walk on directed graph as proposed by Dr. Carly Technomo. This video is part of a series of tutorials on research output in graph theory related to transportation science. Have you ever been stuck in traffic? Hours and hours on the road, roads filled to the brim with honking cars. This is day-to-day life for many people, once in the morning and once in the afternoon when they go home. Sometimes authorities attempt to solve these problems by creating new roads, widening existing roads, making certain roads one-way, adding or removing U-turns, new stoplights, among many others. Sometimes it works, sometimes it doesn't, and they try another method. And that doesn't work either, so they come up with a new one, so on and so forth, but the traffic still remains. How do you solve this problem? How do you come up with rigorous, well-informed solutions that will alleviate traffic and maximize taxpayer funds? Traditionally, the flow is modeled by traffic assignment model. We won't go into detail with the processes, but typically it requires data on the travel demand, which is also called origins and destinations data. This OD data requires agencies either to track cars one by one, check which roads they pass by and how long it takes them to pass these roads, or use not so reliable questionnaire surveys. It's a tedious, costly process, even with cameras and sensors. Now, for many countries, the governments may not be able to gather data as effectively, or may not be able to dedicate sufficient resources towards data gathering goals, leaving them with congested roads and trial and error solutions that end up wasting taxpayer funds. In light of these problems, a new method to determine how traffic would best flow in a network was created. This method can provide simulations, whether you have no data at all, just a map of your road networks, or whether you have minimal data, or okay data, or great data. For example, you know that more people need to go to the school than to the park, or that they're more likely to take this road, or that a certain number of cars go through this road at certain times, and there's always this much traffic. And of course, the model will be more accurate the more data there is. But regardless, the model will provide the ability to simulate solutions for real-world traffic problems and avoid unnecessarily wasted labor and funds. The aim was to create an ideal flow based on random walk of multi-agents in a directed network graph. And I'm going to explain to you what exactly this means and how it works. Let's start first with, what is an ideal flow? Basically, how do we make it so that our roads don't have traffic congestion? How do we make our roads more effective and efficient? If you go to the supermarket and there's a long line, you add more cashiers. If you add too many cashiers, there are now idle cashiers. You want efficiency and effectiveness. You want it to be just enough, ideal. And so we're looking for the ideal flow within a network. The next question is, what exactly is a network? Networks such as computer networks, road networks, rail networks, communication networks, a network of blood vessels, are interconnected systems made up of nodes and links. For example, if we made up a city, it would have a network of roads connecting important places. This could be a residential area, a school, an office, a park, a market, for example. These locations are called nodes. That's where people come from and where people want to go. The roads that connect them are called links. Throughout this video, we're going to be using the example of road networks. We'll discuss a few further important points about our network. Our network is directed, which means these nodes are connected with links that have directions. For example, this link goes this way, that link goes that way. Each one could represent one-way roads, or two together would be a two-way road. Our road network is also strongly connected. That is, you can get to any other node from any starting node, and you can also go back home. If I'm at home, I should be able to go to the school, the office, the market, the park, and from those other places, I can also go everywhere else. We're also going to assume that there will be conservation of flow. So if 6 cars go to the park, these 6 cars have to leave the park eventually. Cars can't just appear out of nowhere or disappear into the park. Apart from that, although this isn't necessary for all ideal flow networks, because we have no data and we only know the structure of the road networks, we're going to assume that we have uniform distribution. If there are 2 roads, there is an equal probability that a car will choose either road. In real life, or if we knew more about the city, this road might be dilapidated or there might be a toll, so the agents may prefer to choose one road over the other. For our current simulation, we're going to assume that our agents don't care either way. In a future video, we will show how to use non-uniform distribution. Now let's talk about random walk of multi-agents. So imagine at each node, there are a certain number of agents. For our example, our agents are cars. These are multi-agents, so there are many cars at every node. The cars want to go to the other nodes. They could take any of the roads available to them, and because we're using a random walk simulation, they're going to choose randomly. Each time a car passes through a road, we count. We let them do this random walk over and over again. The idea is that the more times they do this, the closer it's going to get to the real values. And so we want the number of times we do this to approach infinity. As we can't really do it an infinity times, a sufficiently large number will do. 1,000 days, for example. Let's say we don't know anything about the city. The roads are there, that's all we know. We don't even have to know how many times each individual road was passed through. If we know 2, for example, that the car passed through this road 1,000 times and 250 cars passed through this road. So since 1,000 cars passed through this road to this node, and there are only 2 exits, then 500 must have went to each. 250 here, so another 250 here. 2 more exits for the 250 that entered, so 125 for each road. 125 here, since there's only 1 road, and all these roads went here. And if you count it, it adds up to 1,000, where we started. These numbers, they're called flow. And then, since these are big numbers and messy to deal with, we can actually divide these by the smallest number for simplicity. Given this network, these numbers would then be our ideal flow. What do these numbers mean? In a steady-state condition, they are the ideal amount of flow through the links. Congestion would then be the function of this flow over capacity, the actual capacity of the road. Capacity can be represented by road width. For our example, we assume all roads have the same capacity, thus the flow indicates the congestion level of the road. In a future video, we will show how to handle roads with unequal capacities. The ideal flow matrix exists based on merely the network structure and the probability distribution of where the agents move towards using random walk. It doesn't depend on origin-destination demand, on the amount of agents, or the amount of time that passes by. It doesn't matter how many cars there are or how long it goes on. It's the structure of the network that must be developed. So far, we've been computing everything manually. It can get very complicated, especially as real road networks have much more nodes and links. There's an easier way to deal with this. We're going to go on to our main theorem, that the ideal flow matrix is always a pre-magic matrix. Magic matrices are these square matrices, for example, a 3x3 square, where it adds up to the same number whether you add the rows, the columns, or diagonally. Pre-magic matrices are similar. They're a square matrix where the vector row sum is equal to the transpose of the vector column sum. If you add these, it's A, and if you add it here, it's also A. Let's go back to our network of roads. Every road will be a value on the matrix. There are 5 nodes, so our matrix will have 5 rows and 5 columns. The rows are our starting nodes, where you're coming from. The columns are our destinations. The first row, starting from the first node, it's 0 because you're not really moving. 2 to get to the third node, so on. We can repeat this for the rest. An ideal flow in a directed network will always be a pre-magic matrix. This is true because, as we said, the flow is conserved. So if 8 agents go into the node, the vector sum of the first row, then 8 agents must also leave the node, the vector sum of the first column. You can compute for ideal flow entirely with linear algebra without even having to go through the process of simulating a random walk. In summary, we discussed, through an example of road networks, how a model of ideal flow was created based on a random walk of multi-agents in a directed network graph. We found that the ideal flow matrix depends entirely on network structure, and that this ideal flow will always be a pre-magic matrix, and can be computed through linear algebra. The ideal flow on a network can be used for a variety of applications beyond road networks. But for our purposes, an ideal flow model on a network provides a simpler, less data-intensive and resource-intensive method for traffic officials and researchers to come up with solutions for road congestion. I hope you enjoyed this video tutorial. You can also visit other tutorials from Dr. Cardy's website, people.reveledu.com/Cardy, and the Ateneo Pedestrian and Traffic Computing Laboratory, pinoy.admu.edu.ph/-pedfab. Thank you for watching.